We have a patient, Mr. Bakshi. He is severely ill, having severe watery diarrhea since morning. What do you think? What IV fluids you are going to give him? The first question arises: when you give an IV fluid, where will the fluid go into his body? That means, where will the IV fluid be distributed in his body? In the human body, the total body water is divided into fluid compartments between the intracellular fluid compartment and the extracellular fluid compartment. The extracellular fluid compartment is divided into the interstitial fluid volume. That means it is the fluid that is present outside both the cells and the blood vessels. And the second one is the intravascular fluid volume. That is the fluid that is inside the blood vessels. This diagram represents total body water content of a person. Out of this total amount of water, 2/3 belongs to the intracellular fluid space, and the rest 1/3 belongs to the extracellular fluid space. For example, if a person has a total body water of 60 liters, then if we divide this total water into 3 equal parts, then we have 20 liters in each part. Out of these 3 parts, 2 parts, that is 40 liter, will belong to the intracellular fluid space and the rest will belong to the extracellular fluid space. In this 20 liters of extracellular fluid, 75% of it, that is 15 liters, will belong to the interstitial fluid space, and the rest 25%, that is 5 liters, will belong to the intravascular fluid space. By intravascular fluid, we mean the plasma. Let us summarize this again. Total body water is 60 liter. The intracellular fluid is equal to 2/3 of it, that is 40 liters. Extracellular fluid is 1/3 of the total body water, that is 20 liters in this case. Out of this 20 liters, 75% is in the interstitial fluid compartment, which is equal to 15 liters. And the rest 25% is in the intravascular fluid space, which equals to 5 liters. Here I have a question. The total body water of a person was found to be 45 liters. How much is the extracellular fluid volume? You have 30 seconds to answer. Your time starts now. The answer is 15 liters. I hope you have answered it by now. Here is the second question. The total body water of a person was found to be 45 liters. How much is the plasma fluid volume? Let me start the timer again. Your time starts now. Here is the solution for you. We know extracellular fluid is equal to one-third of the total body water. That is one-third of 45 liters in this case. That equals to 15 liters. We know that plasma is equal to 25% of the extracellular fluid. That is 25% of 15 liters, which equals to 3.75 liters. So the choice D, 3.75 liters, is the answer. Easy, isn't it? One big question. How much is the total body water? How can we know it? The clue to total body water is in a person's weight. 60% of the weight of a person is his total body water. The body water content based on weight varies in male, female, and children. In female, it is said 50 to 55% of the weight is the total body water. In men, 60 to 65% is the total body water, and in children, it's around 70%. But for simplicity, in clinical practice, 60% of the weight of a person is considered as the total body water content. In this example, if the weight of a person is 70 kilograms, then total body water will be 60% of 70 kilograms, which is equal to 42 liters. The intracellular fluid will be two-thirds of total body water, which is equal to two-thirds of 42 liters. That equals to 28 liters. Extracellular fluid will be one-third of total body water. So one-third of 42 liters will be 14 liters. Out of this 14 liters, plasma is 25% and interstitial fluid is 75%. So if we equate it out of 14 liters, we get plasma around 3.5 liters and interstitial fluid around 11.5 liters. In this diagram, on the left side, we see a single cell. This represents the intracellular compartment, and on the right side, we see a part of a blood vessel. This represents the extracellular compartment, especially the intravascular compartment. The blue circles represents water molecules. They are same on both the compartments, that is the intracellular compartment and the intravascular compartment. The red circles represents other solutes. They are also equal on both the sides. So we can say that both the compartments are in equilibrium with respect to number of water molecules and the number of solutes. Our patient, Mr. Bakshi, is losing water due to severe watery diarrhea. This results in loss of water component in the plasma. Now we can see that water content in the plasma has depleted and the water content of the intracellular compartment is more as compared to the plasma water content. So, water from the intracellular space will now get into the plasma space to compensate the water loss or to bring equilibrium on both the sides. Due to the excess loss of water from the intravascular space, the water content gets depleted within the plasma. So, the intracellular space comparatively has more water as compared to plasma. This excess water will enter the intravascular space to compensate the water loss, so that water concentration on both the sides becomes equal. Now we can see that there is same amount of water on both the sides. But due to the loss of water from within the intracellular compartment, the cells will shrink due to the loss of cell turgidity. Suppose we select to give our patient Mr. Bakshi plain water as IV fluid. At first, water will enter the intravascular compartment. Then, after a certain time, accumulation of excess water will take place in the plasma. Now, due to this excess water content of plasma, the water will pump into the intracellular compartment. This will help in restoring the cell water content and will in turn restore the cell volume. But if you keep administering more water continuously into Mr. Bakshi's intravascular compartment, then the excess water will also enter into the intracellular compartment. This will result in more water content of the cells. They will start to swell and finally burst out. That means it will bring trouble for our patient, Mr. Bakshi. So, how much IV fluids we will give to our patients will depend on the concept of the concentration. That is, the concentration of the fluids in the fluid compartments of the body and the concentration of the IV fluids that are available to us. Before we proceed further, we need to brush up the concept of concentration of a solution. Concentration of a solution is the abundance of a constituent, that is, the solute, present in a specific volume of a solution. It is expressed as molar concentration, which means moles per liter of a solution. So, what does a molar concentration of a solution mean? It means moles of particles that are present per liter of a solution. Therefore, 1 molar solution is equal to 1 mole of particle per liter of a solution. For example, if we put 1 mole of sugar in 1 liter of a solution, then the solution will be 1 molar sugar solution. In this example, we have 4 particles or molecules. Let us say that each particle represents 1 mole. Now, if we put it inside a liter of a solution, then we can see that these 4 molar particles will dissolve to form a 4 molar solution. Look at this example. Suppose each molecule of these represent 1 mole of particles, and now if we drop 4 moles of these particles into the solution, see what happens. Though we have made a 4 molar solution, but each particle splits into 3 particles. Now let us compare both these solutions. Remember, each particle in this example represents 1 mole of the substance. In both the cases, we placed 4 moles of the substance in a liter of water. Both the solutions are 4 molar solution, but there is a difference between the two equimolar solution. The 4 molar solution on the left has 4 moles of solute in it, but the 4 molar solution on the right side has 12 moles of solute in it. This example shows a 4 molar glucose and a 4 molar calcium chloride solution. In both the cases, we have 4 moles of each into 1 liter of water. When we compare them, we see that 4 moles of glucose rendered 4 moles of solutes in the solution, but 4 moles of calcium chloride formed 12 moles of the solute. This is a big disadvantage when we try to express body fluids or IB fluids as molar concentrations, because the number of particles in a solution affects the property of the solution, that is, the osmotic property. Like in the above examples, we can see that both are same molar concentration, but a molar concentration does not give the clue how much number of particles are finally in a solution. That means we cannot know the osmotic property of the solution. Before we talk about osmotic concentration, let us revise the perception of osmosis. Osmosis occurs when a selectively permeable membrane is placed between two solutions so that only the solvent is allowed to pass except the solutes. In this example, we can see that the number of particles on either side of the selectively permeable membrane is same, so both the solution are in balanced state. Now, in this example, we can see that there is more number of solutes on the right side. As a result of this, there is less water potential on the left side as compared with the right side. This difference in the water potential causes osmosis to occur, because we know that water from higher potential will always flow towards the lower potential. This is a natural phenomenon explained in physics, which states that energy flows from higher potential towards lower potential. But for the energy to flow from lower potential to higher potential, additional energy will be required. Since osmosis is a passive process, so water flows from higher potential to a lower potential. As a result of this, equilibrium is achieved. So, we can say that osmosis is the spontaneous movement of solvent molecules through a selectively permeable membrane from a region of higher water potential to a region of lower water potential that will ultimately equalize the solute concentration on both the sides. Here you can see that the solvent has entered from the left side towards the right side, so that the volume of the solvent on the right side increases. This results in the reduction of concentration on the right side, which equals to the concentration on the left side. Thus, equilibrium is achieved. Now, let us learn osmotic pressure. Here we have water separated by a selectively permeable membrane. Now we introduce some sugar on the left side. This will result in increase of concentration of the left side and decrease in water potential as compared to the right side. So, water from the right side will enter the left side. Now, if we place a piston on the left side and apply force to it, the water flows back to the right side again. Thus, we can say that the piston has counteracted the force of water that was trying to enter from the right side. This counteracting force is the osmotic force. Thus, we can say that the osmotic pressure is the minimum pressure which needs to be applied to a solution to prevent osmosis. Osmotic pressure is directly proportional to the number of particles present in the solution. It is not affected by the type, valence, and weight of the particles. Osmotic pressure can only be possible when impermeable solutes are present in a solution. Osmole is the unit of osmotic pressure. 1 osmole is defined as 1 mole of any non-dissociable substance. Here we have 1 mole of glucose in 1 liter of water, which means we have 180 grams of it, that is 6.022 into 10 to the power 23 number of molecules of glucose is present in 1 liter of the solution. Since glucose does not dissociate further in the solution, so we can say the concentration of the solution is 1 osmole of glucose. In this next example, we have 1 mole of sodium chloride that will dissociate into 1 osmole of sodium and 1 osmole of chloride in 1 liter of solution. Therefore, 1 mole of sodium chloride will form 2 osmoles of the solution. In this example, we have 1 mole of calcium chloride that will dissociate into 1 osmole of calcium and 2 osmoles of chloride in 1 liter of a solution. Therefore, 1 mole of calcium chloride will form 3 osmoles of the solution. In this example, we have a molecule named WXYZ, which splits initially into 3 parts, but then again, the Y part further splits into another 2 parts, A and B. Therefore, we can say that 1 mole of WXYZ is equal to 4 osmolar. When we say osmotic concentration, it means how many osmotically active particles are present in a given amount of a solution. When we express the osmotic concentration as number of osmotically active particles in a liter of a solution, it is called osmolarity. And when osmotic concentration is expressed in a kilogram of the solution, then it is called osmolality. When we say osmolarity, it means liter of a solution. Letter R of liter, so osmolar, osmolar, liter. Mind the letter R. When we say osmolality, it means kilogram of the solution. Kilo osmol, kilo osmolality, letter L for kilo, osmolality, LL for lity. So, we know now that osmotic concentration can be expressed as osmolarity or osmolality. Osmolarity is expressed as osmoles per liter and osmolality is expressed as osmoles per kilograms. There is downside of osmolarity. Osmolarity changes with temperature. Solutes and solvents volume changes with temperature, so the osmolarity value will change too. In clinical practice, we use osmolarity mostly because when we administer drugs or analyze fluids, we think in volume units like milliliter, liter, or deciliter, etc. So, osmolarity is good enough for clinical use. Whereas osmolality is a static measurement unit, since solutes and solvents are not affected by temperature. So, osmolality is mostly used in laboratory or lab values. Here is a question for you. We have 10 moles of magnesium chloride in a 5 liter of a solution. What is the molar concentration and osmotic concentration of the solution? Your choices are these. Let me start the timer. Your time starts now. Here is the solution for you. One magnesium chloride molecule in a solution dissociates into one magnesium ion and two chloride ions. Therefore, when we express it in concentration, then we will say one particle of magnesium chloride will dissociate into three particles. Therefore, 10 moles of magnesium chloride will form 30 osmoles in a solution. Now let us convert magnesium chloride as molar value by dividing it with 5 liters. Similarly, we convert the solution's osmolarity of the particles by dividing it with 5 liters. Therefore, we get that 2 molar solution of magnesium chloride will be 6 osmolar solution. Hence, the answer will be D, that is 2 molar and 6 osmolar. So, osmotic concentration can be expressed as either osmolarity or osmolality. It reflects the relationship between the solutes and the solvents. Remember, osmolar means R, means liter. Osmolal means L, means kilo. Here, we have a 500 ml of normal saline. The question is, how much is the osmolarity of this 500 ml bottle? We know 0.9% sodium chloride means 9 grams of sodium chloride per liter of solution, which means 9,000 milligram per liter. First, let us find the amount of sodium chloride present in millimoles per liter of the solution by using mole formula. Total weight 9000 milligram is divided by the molecular weight of sodium chloride, which is approximately 54.5. Therefore, we get the concentration of sodium chloride as 154 millimoles per liter. We know that 1 millimole of sodium chloride will form 2 millimoles of its dissociated ions. So, 154 millimoles of sodium chloride will give 154 millimoles of sodium ions and 154 millimoles of chloride ions. They together will make 308 millimoles of sodium chloride particles. Therefore, we can say that 1 liter of normal saline has an osmotic concentration of 308 milliosmoles. Remember, 500 milliliter of the solution of normal saline will have the same concentration as 1 liter because concentration is a measure of specific unit. When we say osmotic concentration, it means osmoles per liter or per kg. So, even a 200 ml of normal saline will have the same osmotic concentration as 5 liter normal saline 0.9%. By the end of part 1 and part 2 lectures in IV fluid series, we have cleared the following concepts. The concept of mole, which is an estimate of number of particles of ions or molecules or atoms. Then we learned about the concept of equivalent, which measures the chemical bonding activity of an electrolyte in a solution. It is simply derived by multiplying moles of ions present in a solution with their valence. In this part 2 of the series, we learned about the meaning of concentration of a solution, the unit of which is molar concentration. Then we learned the basic concept of osmosis, and finally we learned what is osmotic concentration of a solution. Remember, Mr. Bakshi is still having watery diarrhea. Can we administer fluids to him now with the knowledge that we gained so far? No, we need to know many things more, like comparison of osmotic concentration along with the concept of tonicity. We need to know osmotic concentration of the body fluids. We also need to know what are the types of IV fluids that are available and their respective osmotic concentrations. Then only we can do something for Mr. Bakshi. Mr. Bakshi needs your help, so let's go and watch the next part of this video. Thanks for watching. Please like, comment, share and do subscribe to my channel. Click the bell icon in order to get updates about further videos that I'm going to post for you.